Thanks. So that was the previous title, so I also changed it. I'm going to talk about Bohmian mechanics and cosmology, but I'm going to talk about one aspect of it. So I'm going to suggest to you a new way of making a semi-classical approximation to quantum gravity based on Bohmian mechanics. Okay. But before I go to that, I want to also make some publicity about previous work I've done on Bohmian mechanics applied to cosmology. And the first thing is the quantum to classical transition in inflation theory. So Daniel Sudarsky explained the problem that arises in standard inflation theory. All large-scale structure is supposed to come out of vacuum fluctuations. The standard law is that these vacuum fluctuations during the expansion of the universe somehow grew into classical perturbations. How exactly does it go? Daniel Sudarsky proposed solution. He looked into collapse theories. You can also look at the problem from the point of view of Bohmian mechanics. Okay? In Bohmian mechanics, I'll say more what Bohmian mechanics is later on, but in Bohmian mechanics, there's more than just a wave function. There's also an actual particle positions, or in the case of inflation, there's an actual field. Okay? And while the quantum state vector can be homogeneous and isotropic, the actual Bohmian field is not going to be isotropic and homogeneous, okay? And you can also study the classical limit. You can see when exactly this Bohmian field becomes classical. And when you do the analysis in the context of inflation theory, you see that this Bohmian field exactly becomes classical or starts to behave classically exactly where you would expect it when the modes cross the horizon. And you get the correct statistics. So what people usually do in inflation theory, you can give a conceptually clear account for that within the context of Bohm theory. The other thing, so I did this work with Nelson Pinto-Neto and Santos. The other thing we recently looked at is singularities in quantum gravity. So we only considered mini superspace models, but what's the point here? Well, in Bohm, when you apply it to quantum gravity, there's not only the wave function, but there's also an actual metric, okay? So it becomes a clear question whether your space-time has singularities or not. You look when the space-time, when the Bohmian metric becomes singular or not, okay? And the interesting thing is that we looked at mini superspace models. The interesting thing is that you get different results, for example, compared to consistent histories in certain cases, okay? When you look at Wheeler-DeWitt quantization, consistent history says that you're always going to run into a singularity. According to the Bohmian approach, there's always a non-zero probability that you don't run into a singularity, okay? When it comes to loop quantum gravity, so one of the main selling points of loop quantum gravity is that you never have a singularity, okay? Here, the Bohmian case, as far as I can tell, and consistent histories would agree. Indeed, you never run into a singularity. Okay. Now let me move on to semi-classical approximation. So that's stuff I'm recently working on. That's work in progress, so I'd love to hear your feedback on this. What's the motivation? Well, the motivation is basically the search for quantum gravity. It's one of the holy grails of physics, to find a quantum theory for gravity. There's a number of approaches, and there's a whole lot of difficulties. For example, if you look at just standard way of quantizing general relativity, so canonical quantum gravity, you get what's called the Wheeler-DeWitt equation. That equation is very hard to solve. It also has some conceptual problems. For example, the problem of time. If you look at this equation, you would expect here a time derivative of psi on the right-hand side, but that's 0 in this case, so the wave function is stationary, it doesn't evolve in time, so how can we account for the appearance of time evolution? So for that reason, people often look at semi-classical approximations to quantum gravity, just to get a handle on what one might expect if we, instead of solving the full quantum gravity, maybe we can already make some predictions using semi-classical gravity. Okay. And what's the usual approach to semi-classical gravity? Well, you consider gravity classical, described by Einstein field equations in the lower part. So you have a classical metric, little g, and you describe matter quantum mechanically, just as quantum field theory on curved spacetime. Okay? So, for example, for a scalar field, you have a certain wave function for the scalar field. Its time evolution is given by a certain Hamiltonian, which depends on the classical metric little g. And the matter acts back on the metric in Einstein field equations through an expectation value of the energy momentum tensor. Okay? Now, we know this is going to be a good approximation if matter and gravity behave approximately classically. But if matter behaves, but it's going to break down in certain cases. So for example, when the matter is in a superposition, in a macroscopic superposition, the expectation is that this semi-classical approximation is going to break down. Why is that? Well, suppose you have a macroscopic superposition, say, of the sun being located at one place, plus the sun being located at another place. So psi1 is the sun at one place, psi2 is the sun at the other place, and the energy densities corresponding to psi1 and psi2 would look something like that if you had them separately. If you look at the energy density corresponding to the sum of the two, psi1 plus psi2, you get two lumps, okay, which are half the size of these densities corresponding to psi1 and psi2. So this energy distribution with these two lumps is going to appear in Einstein's classical equations, okay? So what you're going to get is like self-gravity. These lumps are going to gravitate to each other. This is not what you would expect from a full quantum theory of gravity. What you would expect is the lump is going to be either here or there with its own gravitational field, okay? There's also an experiment by Don Pacher and Geilker, which actually rules out that exactly that kind of semi-classical approximation. So again, for sure, this is just an approximation. It's valid in a certain domain. It cannot be generally valid. Okay. What's the main idea now? Well, in Bohm's theory, we have more than just a wave function. Okay? In the case of just a scalar field, there's an actual field configuration. Okay? There's an actual field in space. How it moves over time is determined by the wave function. This field in space also determines an energy momentum tensor. So instead of using the expectation value of this energy momentum tensor operator, why not use this Bohmian energy momentum tensor? Okay? And at least such a setup would solve the problem I've just mentioned. If the wave function is in a macroscopic superposition, still the Bohmian field is either going to be at one place or at the other place. Okay? So if you use the Bohmian energy momentum tensor in the classical Einstein field equations, you won't have this problem with macroscopic superpositions. Okay? So the Page-Geilker experiment doesn't immediately rule out this theory. Okay? So this is the main idea. This thing, as I've just explained, doesn't immediately work. The reason is this energy momentum tensor, this Bohmian one, isn't covariantly conserved. Of course, I need a covariantly conserved energy momentum tensor there. Something similar happens if I would look at scalar electrodynamics, for example. I have a scalar field interacting with an electromagnetic field. We could consider the electromagnetic field to be classically, and it could couple to the Bohmian charge current. Okay? Again, I can't do this naive procedure because the Bohmian charge current is not conserved. Okay? The thing is, what I'm at now is I know the way to solve this problem. Okay? The naive thing is just not good enough. What I can do is look at the full Bohmian theory for, say, quantum electrodynamics, and then derive a semi-classical approximation. And then I get some correction terms. I just don't get this naive Bohmian charge current. I also get an extra part to the charge current which is of some quantum nature, okay? And that makes the theory consistent. Okay. So for the rest of the talk, I will say a bit more about Bohm theory, and then I'll say something more about relativistic semi-classical approximations, and then say very briefly something about scalar electrodynamics and linear superspace theory. Okay. So this theory, well, it goes under a lot of names: pilot wave theory or the Breuil-Bohm theory. In a non-relativistic version of it, you have just particles moving under the influence of the wave function. So the actual world is made out of particles. How they move is determined by the wave function. The wave function just satisfies Schrödinger's equation, just the usual equation. And the particles move according to such a law, a first-order law in time. Velocities, you see here on the right-hand side, these are determined by the wave function. And they're of this form. Basically, you can write the velocity as just the gradient of the phase of the wave function. Okay. These are trajectories for a double slit experiment, for example. The theory gives you exactly the same predictions as quantum mechanics, given that these particles have a certain equilibrium distribution. Okay. Two important things in this theory that allow me to get to these semi-classical approximations are the following. So, first of all, in a Bohmian universe, you have the wave function of the universe, and you have a collection of particles. So the first important thing in this theory is that you can define the wave function of a subsystem within the universe. And the way you do it is, suppose you just have a two-particle system. So you have a wave function and two Bohmian positions. So Bohmian positions are always, so actual positions are always denoted by capitals. The argument of the wave functions are little x's. The wave function of, say, particle 1, to get the wave function of particle 1, you just take the wave function of the composite system and you plug in the actual position of the second particle. Okay? So this is a natural way of defining a wave function of a subsystem, given that you have the wave function of the whole universe and the positions of the particles. And why is it natural? If you look at the velocity for the particle of the subsystem, it doesn't matter if you use the wave function of the universe, psi, or you use this conditional wave function, this wave function of the subsystem, chi. Okay? So the velocity law doesn't change. So this is one thing. You can define the wave function of a subsystem in an unambiguous way. The second thing is, it's easy to study the classical limit, or at least the question is easily phrased. Why is that? Well, if you look at the equation of motion, the Bohmian equation of motion, this first order equation, you can take another time derivative. You get something that looks like Newton's law. Newton's law with an extra potential. Okay? Q, the quantum potential. So you can see whenever this extra term here is negligible compared to the rest, you have classical trajectories. Okay? Now let's go to semi-classical approximations in a non-relativistic domain. So the usual way you would do a semi-classical approximation, and it's often used by quantum chemists, is as follows. So this would be the equivalent of the usual semi-classical approximation to quantum gravity. So you consider a quantum particle that is described by a wave function. So I label this by 1. This wave function satisfies Schrödinger's equation, where the potential depends also on the position of particle 2. And particle 2 satisfies Newton's equation. Okay? So if I look at the force for particle 2, which is just the gradient of the potential, and I average over the quantum particle, so I have here the distribution, the quantum distribution for particle 1, I average this classical force over this quantum particle, I get my force for particle 2. Okay, so this would be the usual semi-classical approximation. In the Bohmian case, well, in the Bohmian approximation, while you have more stuff, according to the Bohmian formulation, you have also an actual particle for the quantum system, I call it, it has a position, capital X1, okay? And now I can, instead of having this force law, I can introduce this other force law where the force now depends on the position of particle X1, okay? So you can see what's the main difference here. In the usual semi-classical approximation, you take some kind of average, okay, over the quantum stuff. Here, there is no average of that sort. So here, in the usual semi-classical approximation, you kind of average over the quantum fluctuations. Quantum fluctuations don't really have an effect. In the Bohmian case, well, this position for the quantum particle, this Bohmian position, varies, okay? I have to choose an initial distribution for this quantum particle. So this different x1s, different positions for the Bohmian particle are going to give you different results for the classical particle. So in this model, if I want to do statistics, I only do it in the end. And the classical particle always feels like the quantum fluctuations of the quantum particle. Okay? Good. So this suggests that this Bohmian approach is better than the usual one. And that's exactly what quantum chemists found. So quantum chemists have used this Bohmian approximation and they've compared it to the usual one. Okay? And this is basically the first paper that appeared on this. And what they do here is they consider a heavy classical particle, okay? And they consider a light particle scattering off this heavy particle. The light particle is described quantum mechanically, okay? And they just look at the time it takes for this light particle to come back. And the exact result is this line with circles. The solid line is the Bohmian result. So the exact result, so if you treat everything quantum mechanically, is this line with circles. The Bohmian result is this solid line here. If you do this Bohmian semi-classical approximation, the dotted line is the usual semi-classical approximation. So one thing you see is that the exact result, if you wait long enough, the probability is 1 for the particle to come back, this quantum particle to scatter back. In the usual semi-classical approximation, it never reaches 1. So the Bohmian approximation, you get this result back. So also in the Bohmian case, you get that the particle always scatters back at some point. So this is one setup where you have a better approximation using the Bohmian model. There's many more comparisons that have been made between the usual one, the Bohmian one. What they found is either they give comparable results or the Bohmian one gives you better ones. So for me, that gives you some good hope that if you want to apply this to semi-classical gravity, that you might find something interesting, that you might find some new novel prediction you don't have in usual semi-classical gravity. Okay. Very briefly, because I probably don't have much time, how do you derive this Bohmian semi-classical approximation from the full approximation? Well, basically, you just look at this conditional wave function, okay? This conditional wave function of one particle, you just take a time derivative, and then you get something like the Schrödinger equation we saw on the previous slide, and you just get an extra correction. Okay? In addition, if you look at the law of motion for the second particle, take another time derivative, you get this Newton's law with this extra quantum force. So whenever these two terms in red, I'm not sure you can see it, it's red. Whenever these two terms in red are negligible, you get to this Bohmian semi-classical approximation. Okay? So that's what I've done in quantum electrodynamics. I won't go through this. That's what I've done in quantum electrodynamics. So here there's a bunch of equations. You don't need to read them all. So the important thing is when you look at Maxwell's equation here, these are classical Maxwell equation, it decoupled to the usual Bohmian current, plus there's some extra current, which is of quantum nature, it depends on the wave function, which makes that this whole semi-classical approximation is conserved. The important thing here was that I somehow eliminated gauge. I have to work with gauge-independent degrees of freedom, or I have to choose a gauge. Then I can get this consistent semi-classical approximation. Okay? If I don't eliminate the gauge, I don't know how to get to a consistent semi-classical approximation. Now, in quantum gravity, it would be harder to eliminate the gauge. Here you have also gauge, there's diffeomorphism invariance. Eliminating diffeomorphism invariance is notoriously hard, so I don't immediately have a semi-classical approximation for full quantum gravity. But you can have semi-classical approximations if you have simplified models, say for example mini superspace models. You assume homogeneity and isotropy of the metric, you have a homogeneous field. How much time do I have?
Minus 1 minute.
Okay. So, for example, what I get here then, it's my second to last slide, so won't go through this, but the result you get is like a modified Friedman's equation, you get an extra correction, which is just again this quantum potential. So I don't know what exactly the consequences would be for certain wave functions. So maybe one speculation you can make is if this thing is constant, you could get a cosmological constant for free. Okay. So this is the situation I'm at so far. So you can do these Bohmian-based semi-classical approximation for non-relativistic systems, quantum electrodynamics, mini superspace models. You could also do them mini superspace models with fluctuations on top of them. So that would be relevant for inflation theory. So now the interesting thing would be to find some applications. Where can I apply these Bohmian semi-classical approximations and possibly make some new predictions? Okay. These might be found in inflation theory maybe. Maybe if you look at black hole physics, might also be something done. I don't know. Thank you.
Well, we are into negative time, but if there are any very quick negative time questions, they would be welcome. So do I understand then there is actually positive evidence, you're saying, from this experiment in 2001 for the Bohm?
Well, it doesn't confirm Bohm, right? It just tells you that Bohm gives you an approximation scheme that is not available in usual quantum mechanics.
I see.
Okay.
Fine, thank you. Okay, well, since we're running short of time, let's just thank Board again.